Hello, and welcome back to our Summit BIM podcast series, Data Matters. Today, I'm going to be focusing specifically on LOD and the challenges associated with this concept. A couple of months ago, I posted a blog discussing LOD. Level of data, level of development, level of detail, or just level of disorder. The role of LOD within a BIM process is frequently misunderstood and causes considerable confusion. Looking from the perspective of those who procure and operate facilities, how does one specify in an RFP what's needed in a way that can be managed, audited, and built upon to form a rich data set capable of supporting a project throughout its entire life cycle? Remember, this rich data set is far more than a set of record 2D drawings. So let's go back to the beginning and where the concept of LOD came from. Where did it come from and how was it originally used? LOD is a concept borrowed from the gaming industry, where the LOD of a modelled object was initially defined by its proximity to the viewer. The closer an object was to the viewer, the more detail was required to generate a feeling of reality. To reduce mesh complexity and limit the amount of information to be processed by the computer, a range of required detail for the geometry was established, with the closest, most highly developed geometry, level of detail set as LOD 0. Of course, this is the opposite to the AEC-00 industry, where LOD 0 or 1 or 100 is considered minimal geometry. While borrowing the concept of LOD was reasonable in the early days of BIM, as the industry, technology, and complexity of projects evolves, the way we use LOD also needs to change. LOD, short for both level of detail and level of development, is a hot topic. As building information modelling BIM becomes more prevalent across the AEC-00 industry, the use of LOD terminology can lead to confusion around what is being asked for and therefore what needs to be modelled by the team. LOD, remember, refers only to the required geometry, not the data, and is non-specific as to what is to be provided by whom and when. This generality and lack of clarity creates challenges. Sadly, quite often we also come across the requirement for an LOD 300 or 350 model. This assumes that all aspects of the model require the same level of geometry. Again, a diversion from the original concept, whereby, depending upon need, the LOD should change. Shouldn't there be a gradation depending on criticality or risk for defining the required accuracy of the provided geometry to drive a use such as virtual coordination? In a digital, data-driven process, in addition to defining the geometric requirements, we must also consider and define the data requirements for projects. This means we must not only define the geometric requirements for objects based on their purpose, goal, and downstream uses, but also what are the associated data requirements. It is vital to understand that the geometry and data are of equal value. The one does not work without the other. The geometry is the host for the data. Very rich, extensive data can be associated to simple geometry, and likewise, complex geometry may have minimal data. The concept that FMO requires complex geometry, i.e. LOD 500, is not reflective of what the facility management teams that look after facilities throughout their life cycle and on into decommissioning ask for. Let's be clear. According to BIM Forum 2023, LOD 500 is defined as follows. The model element is a graphic representation of an existing or as-constructed condition developed through a combination of observation, field verification, or interpolation. The level of accuracy shall be noted or attached to the model element. There is not a single mention of data or installed asset information required for FMO or to drive the concept of a digital twin. So understanding LOD and its limitations. Although at first glance LOD looks like a fairly simple framework, complexity arises when we try to apply it. As mentioned, remember, LOD refers only to geometric representation required to create 2D drawings. It neglects the information associated with the geometry. More complex or detailed geometry does not equal a more developed or valuable model, especially for the owner and facility management team, who need it for the life cycle of the project. The value add comes when we associate structured data with the geometry. If you're just beginning with LOD, start with a process that we call identify. By specifically identifying the required information to be derived from or associated with the geometry. Ask yourself, what is the information we want from placing geometry? Is it size, location, level, orientation, clearances, and don't forget appearance? Remember, not all geometry requires the same data parameters to be associated with it. What data do we need to be associated with what geometry? Classification, name and number, type mark or mark. There is a long potential list of data fields. Likewise, what is the information going to be used for? Different uses require different aspects to be precise. Estimating, for example, requires an accurate count, identification and sizing of elements, whereas for virtual coordination, important not only for construction but also for maintenance and operation, location, size and clearances for installation, operation, maintenance access and replacement are all vital. Some uses require all outputs, others only some. How are you going to define and organize your requirements? Another variable to consider is when. During the process of design and construction, is this information required? Some aspects are required to drive the design process, and others pre-construction, fabrication, and/or the life cycle and facility management. This evolution has been identified in ISO 19650 as the level of information need and considers both data and geometry. So what is the level of information need? Introduced in ISO 19650-1, the level of information need expands the scope of information collected from geometry to alphanumerical information and documents. The alphanumerical information is considered equally as important as geometry, since it forms one of the most important outputs of a project. It is absolutely vital if we want to even consider or talk about the concept of a digital twin. The level of information need for each information deliverable is determined according to its purpose. This includes determining the quality, quantity, and granularity of information. This can vary from deliverable to deliverable, based on design, construction, and handover needs. It tends to be unique with some commonality to the project and client. While assessing level of information need is currently more prevalent in the UK than in Canada, as the ISO 19650 framework becomes more widely adopted here, it will be necessary to redefine the geometry and data requirements based on need, not on what a 2D drawing output looks like. It is hypothesized, and some projects have been undertaken, where the 2D drawing output is not a requirement, but the underlying data sets from the models are. We need to revisit LOD to improve data-driven processes. As the industry moves towards a data-driven process rather than the 2D paper drawing process, it is crucial to revisit LOD and define data and geometry requirements based on downstream uses rather than drawing output that was previously required. In other words, what information do you need to enable what processes to occur, and when during the project timeline from capital planning to end of life? Assigning a blanket LOD to a model may easily result in the over-provision of information that's not strictly needed, or more seriously, the under-provision of information that is vital. The more efficient and effective process, as identified in ISO 19650, is to define the requirements based on purpose, goals, and uses, identifying what aspect of the geometry needs to be accurate. That is, what information is required to be derived from that geometry, what downstream uses will rely on it, and when during the process will it be required. In addition, what data attributes are required to be associated with which pieces of geometry? And again, when during the process does this information need to be available within the dataset to drive the defined downstream uses? Remember, not all pieces of geometry require the same degree of development or data requirements. Those requirements need to be defined. In our experience, LOD terminology can lead to confusion and a lack of clarity as to what is expected from each party involved in the project. For example, the BIM Forum requires LOD 300 geometry to obtain an accurate count, location, or elevation. However, these three attributes do not require complex geometry to drive downstream uses. As the industry's thinking changes from geometry-driven to data-driven, the value of a project will be determined by how structured the data coming from the models is. Structured, that is, in a way that it can be automatically read and processed by another piece of software. To date, the evolution of LOD appears to have been driven by drawing output, not planned data uses. We need to ensure that we are providing the right information at the right time to achieve the defined goals for all project participants, including meeting the needs of facility management. At Summit BIM, we have over the past 15 years evolved a method for managing both geometry, data, and time relative to the project timeline. We've generated what we refer to as a data and geometry specification, a DGS, and a data collection specification, a DCS. These enable us to align with ISO 19650, defining clearly and managing through audits expectation against what has been generated and handed over for the project's life cycle. The data and geometry specification focuses on ensuring that from the owner FM's lifecycle perspective, required assets and their associated data are present in the design intent information and can be captured to support the next step. The data collection specification focuses on installed asset information, both metadata and documents required relative to the various asset types present in the design intent models. These formats enable us to control the requirement and deliverable for the life cycle, ensuring that by handover, the owner has all the information needed to operate the facility. This includes ensuring that the geometry and data supports all defined uses required during the project. Virtual coordination, for example, to ensure that adequate space has been retained for maintenance and replacement. Summit BIM manages this process with our proprietary BIM FMI cloud-based interface, which enables the owner and FM team to view the relevant data in an easily understandable format and helps them to develop preventative maintenance, PM, plans during construction so that by handover they have all the information they require in a digital format to operate the facility from day one. This format for defining and subsequently managing this complex issue has proved to be very successful. It provides assurance that the end users, the client and FM team, have specified what they want, provides the design and construction team the opportunity to understand clearly the expected output and assesses the work effort required, and provides the opportunity for feedback and adjustment in a controlled and managed format. We discussed this in a blog post, DGS DCS Evolution, a retrospective, which is available on LinkedIn and on our website, summitbim.com. LOD is on everyone's mind. I'd encourage you to dip into recent articles on LinkedIn, or please get in touch with us. We'd love to discuss different ways of defining data and geometry and share our evolving approach to managing this complex issue. Without being able to clearly define and manage both the geometry and data, the concept of a digital twin is moot. You can't have the one without the other. Thank you for listening. Having discussed the fundamentals of a BIM process in previous podcasts, the next few are going to take on a slightly different format, so stay tuned.